Alright, welcome back to Geology, and this week we're going to cover Chapter 11, and this is on earthquakes. So what is an earthquake? An earthquake is a vibration of the earth itself, produced by rapid release of energy. Energy is released and radiates in all directions from its source, and we call the source of an earthquake the focus. Energy is in the form of waves, and we have seismometers around the world to record these events, and to accurately measure and determine the location of an earthquake, we need 3 seismometers to record it. So the epicenter is the location on the surface directly above where the earthquake took place. The focus is the actual location of the center of the earthquake, usually a number of miles deep into the earth. And then the seismic waves go out in all directions away from that. Well, we can associate fault lines with earthquakes, and so movements that produce earthquakes are usually associated with large fractures in the Earth's crust called faults. We actually have a fault in Missouri, the New Madrid Fault. Most of the motion along faults can be explained by tectonic theory. Now, there is a theory about elastic rebound as the mechanism for earthquakes, first explained by H.F. Reed. Said that rocks on both sides of an existing fault are deformed by tectonic forces, and that rocks bend and store elastic energy, and frictional resistance holding the rocks together is overcome. In the earthquake mechanism, slippage at the weakest point, the focus, occurs, and vibrations, the actual earthquake itself, occur as the deformed rock springs back to its original shape, hence the elastic rebound. And earthquakes most often occur along the existing faults where the frictional forces on the fault lines are overcome. Here we see a offset here between a fault line along a farmland. We can see how the motion there, the earth has resulted in a significant gap in the fence line there on this person's property. Well, what are foreshocks and aftershocks? These are before and after quakes that occur around the main earthquake. Adjustments that follow a major earthquake often generate smaller earthquakes called aftershocks, and there can be a number of these afterwards. Small earthquakes, called foreshocks, often precede a major earthquake by days or even in some cases as much as several years. Let's talk about probably the most famous fault line in the world, the San Andreas Fault. It's the most studied fault system in the world, goes along Los Angeles. Displacement occurs along discrete segments 100 to 200 kilometers long, or about 60 to 120 miles long. Some portions exhibit slow, gradual displacement known as fault creep. Other segments regularly slip, producing small earthquakes. Still other segments store elastic energy for hundreds of years before rupturing in great earthquakes. And this is a transform fault that we've already discussed, and the process is known as stick-slip motion. Great earthquakes should occur about every 50 to 200 years along these sections. So here's the San Andreas Fault. It's a very long fault line going from Los Angeles and San Diego up to San Francisco and beyond. Well, what are the study of earthquakes? That's called seismology. The study of earthquake waves, seismology, dates back almost 2,000 years to the Chinese. Seismographs are instruments that record seismic waves. These record the movements of the earth in relation to a stationary mass or on a rotating drum or a magnetic tape. So here is this spring with a weight on it and a rotating drum. Now, of course, these days we have more technologically advanced instruments, but this is the basic motion of it. The seismographs, more than one type of seismograph is needed to record both vertical and horizontal ground motion, and the records obtained are called seismograms. So now let's talk about the different types of seismic waves we can have in an earthquake. First, there are surface waves, and these travel along the outer part of the earth. Surface waves have complex motion, cause the greatest destruction, They're also called shaking waves, or S waves. They exhibit greatest amplitude and the slowest velocity. Waves have the greatest periods, the time interval between crests of waves, and are often referred to as long waves, or S waves. We can have body waves. These are traveling through the Earth's interior, and two types are based on the mode of travel. One is the primary P wave. This is a push, pull, compress, and expand motion, changing the volume of the intervening material, and they travel through solids, liquids, and gases. They generally, in any solid material, P waves travel about 1.7 times faster than S waves, which we're going to talk about next, the secondary waves. Shape motion at right angles to their direction of travel, and they only travel through solids. So P waves can go through any part of the Earth, but S waves cannot, like the liquid core we have. The S waves cannot go through that. These are slower velocity than P waves and have slightly greater amplitude than the P waves. So we've already talked about the focus and the epicenter. The epicenter is located using the difference in velocities of the P and S waves. So to locate the epicenter of an earthquake, 3 station recordings are needed to locate an epicenter. Each station determines the time interval between the arrival of the first P wave and the first S wave at their location. A travel time graph is used to determine each station's distance to the epicenter. So here we see a seismograph. We see the first P wave hit, and a few minutes later then the first S wave starts to hit, and then the surface waves hit and cause the most destruction. So to locate the center of an earthquake, the epicenter, a circle with a radius equal to the distance to the epicenter is drawn around each station, and the point where all 3 circles intersect is the epicenter. So here's how we would find an earthquake epicenter. We have 3 stations, Darwin, Paris, and Nagpur. And we find that the location of the earthquake is up there in the mountains. Measuring the size of earthquakes. 2 measurements that describe the size of an earthquake are intensity, a measure of the degree of earthquake shaking at a given locale based on the amount of damage, and magnitude. Magnitude estimates the amount of energy released at the source of the earthquake. Now we use what was called the modified Mercalli intensity scale. It was developed using California bridges as its standards. California buildings. The drawback of intensity scales is that destruction may not be a true measure of the earthquake's actual severity. So this goes from 1 to 12, and this is not the same as a magnitude that we talk about when we have magnitude 6 earthquake. These are just different Mercalli intensity scales that talk about the destruction of buildings that would occur. From 1, we're not felt except for a very few specially favorable circumstances, up to a 12, damage is total, waves seen on ground surfaces, objects thrown upward into the air. Now we used to use the Richter magnitude scale. This is the number you hear about on the news when they say the earthquake had a certain strength and magnitude. The concept introduced by Charles Richter in 1935. It was based on the amplitude of the largest seismic wave recorded and accounts for the decrease in wave amplitude with increased distance. On this scale, the largest magnitude recorded was on a Wood Anderson seismograph was 8.9. Magnitudes less than 2 are not even felt by humans, and each unit of Richter magnitude increase corresponds to a 10-fold increase in wave amplitude and a 32-fold increase in energy. So here are some of these largest earthquakes. This is in your book. You can see that the ones in the 60s in Chile and Alaska were the most devastating earthquakes ever seen. Several Richter-like magnitude scales have been developed, and the one used these days now is the moment magnitude, which is developed because none of the Richter-like magnitude scales adequately estimate very large earthquakes. It's derived from the amount of displacement that occurs along a fault. So let's locate the source of earthquakes. Earthquake belts. About 95% of the energy released by earthquakes originates in a few relatively narrow zones that wind around the globe. Major earthquake zones include the Circum-Pacific Belt, the Mediterranean Sea region to the Himalayan complex, and the Oceanic Ridge system we'll see here in a minute. So here we see what we know as the Ring of Fire around the Pacific. We've seen this before a couple weeks ago. And we see in the Alpine Himalayan Belt a number of other ones. And then you see another one along the Mid-Atlantic Ridge that we've talked about before. Now let's talk about destruction in an earthquake. The amount of structural damage attributable to earthquake vibrations depends on the intensity and duration of the vibrations, the nature of the material upon which the structure rests, and the design of the structure itself. Now, ground shaking includes regions within 20 to 50 kilometers of the epicenter will experience about the same intensity of ground shaking. However, destruction varies considerably, mainly due to the nature of the ground on which the structures are built. For instance, the Ozarks are on cave systems, but the New Madrid Fault is on a sandy system. And so when the New Madrid Fault goes, it's going to pretty much destroy much of Memphis, because Memphis sits on a sandy soil surface. Here is some damage caused by the 1964 Anchorage, Alaska earthquake, a very famous earthquake in history. And here's what I was talking about with Memphis, liquefaction of the ground. The unconsolidated materials like sand, saturated with water, turn into a mobile fluid. We also have seiches, the rhythmic sloshing of water in lakes, reservoirs, and enclosed basins. Waves can weaken reservoir walls and cause destruction. Now, let's talk about tsunamis. This has really only become a big topic recently. But a tsunami is a massive seismic sea wave. It's destructive waves that are often inappropriately called tidal waves, which is really different. That's attributed to the moon. They result from vertical displacement along a fault located on the ocean floor or a large undersea landslide triggered by an earthquake. In the open ocean, height is usually less than 1 meter. In shallow coastal waters, though, the water piles up to heights that occasionally exceed 30 meters and can be very destructive. Landslides and ground and fire can result in this. So we have a tsunami here due to an earthquake, and in the open ocean, you really wouldn't even know the tsunami is taking place. You would just witness a wave go past you, maybe a meter tall, which is very common on the ocean surface. But they can travel very, very fast, past the speed of sound. And so as the water goes up to a land basin, it pushes itself upwards, and then the tsunami slows down. It gets to incredibly high heights. So in 2004, we heard about a massive tsunami that killed hundreds and thousands of people near Sumatra in the Indonesian Ocean. This happened on the day after Christmas, 2004. And here's a picture of the tsunami coming on the shore. Well, can earthquakes be predicted? Short-range predictions. The goal is to provide a warning of the location and magnitude of a large earthquake within a narrow time frame. And research has concentrated on monitoring possible precursors, phenomena that precede a forthcoming earthquake, such as measuring uplift, subsidence, and strain in the rocks. Currently, no reliable method exists for making short-range earthquake predictions. Long-range forecasts, though, give the probability of a certain magnitude earthquake occurring on a timescale of 30 to 100 years or more. These long-range forecasts are based on the premise that earthquakes are repetitive or cyclical, using historical records or paleoseismology, looking at the records in the rocks. They are important because they provide information used to develop the Uniform Building Code, mostly used in California, and they insist on land use planning. A good fit exists between the plate tectonics model and the global distribution of earthquakes. And so the connection of deep focus earthquakes and oceanic trenches is further evidence to that. Only shallow focus earthquakes occur along divergent and transform fault boundaries like we have in California. Earthquakes originate at depths ranging from 5 to nearly 700 kilometers. Earthquake foci are attributably classified as shallow, intermediate, or deep. Definite patterns do exist. Shallow focus earthquakes occur along the oceanic ridge system. Almost all deep focus earthquakes occur in the circum-Pacific belt, particularly in regions situated landward of deep ocean trenches. So here we see a zone of earthquakes, and we see the Tonga Trench here in the Tongan Islands in the ocean, and we see the different earthquakes occurring along that trench in shallow, intermediate, and deep layers. And this is in your book. So we see here along that Tonga Trench out east of Australia and New Zealand, we see some deep earthquakes along with some intermediate. The ones along California are more shallow. That's the end of chapter 11, and now we'll go on to chapter 12.